All right. Good evening. Good morning, Doctor. Called Suzy Joy Ariko. Going to present the models that I trained, the 4 models. So let's dive into the PowerPoint and look through uh, the contents of the presentation. We have the introduction, architecture, how models learn, how they work, optimizer, the results, hyperparameters. We have the conclusion, then the acknowledgement. So for the introduction, all these models are the deep learning models, and they're developed to automatically detect Babesia from the microscopic blood smears. So the dataset contained of the 4 classes, that is Babesia, leukocyte, plasmodium, and the red blood cells. So the 4 models that I trained and evaluated were the EfficientNet, B4, the ResNet 50, the Swine Transformer, and the RegNet Y032. Both models were trained using a transfer learning from the ImageNet. Then the objective was to compare the performances and determine which model would deploy based on the performance metrics. Then the architectures, one was the B4net, and the EfficientNet B4, the ResNet 50, the SWIM transformer, and the RegNet Y032. For each of these, for example, for the EfficientNet B4, it uses compound scaling to balance. Hence, its parameters were the depths, the network depth, the width, and the image resolution. So all these are built under the MP, that is the mobile inverted bottleneck convolution blocks. There are multiple blocks actually following the hierarchy, each where images pass through multiple blocks in order to form what we call a fully layered with the 4 classes classified. So the resolution it takes, it's 380 by 380, and it is designed for the efficient high performance deep learning. Then for the ResNet, it also has the deep, it's also deep CNN, but with 50 layers, hence building using the residual blocks. And also it uses the skip connections to improve the gradient flow, hence preventing vanishing gradient problem. So it takes the image resolution of 224 by 224. Then for the Swine transformer, the hierarchical Bayesian transformer using the shifted window attention, then it processes images as patches. Then it captures both the local and the global context. It also takes the image resolution of 224 by 224. Then for the RegNet, it is a structured CNN designed via the network design space optimization, built using, of course, the bottleneck residual blocks plus the squeeze and excitation. Then it's efficient and it's also a scalable architecture. It also takes the image resolution or the input resolution of 224 by 224. Then how these models learn? As we know, all these models are deep learning models, and therefore both these models learn through supervised deep learning because they use labeled data for learning process. So here we have our learning process in such a way that we input images in a particular network or pipeline. It can be EfficientNet B4 pipeline, the ResNet 50 pipeline, or the Swine transformer, or the RegNet. So we feed in images, then of course the model extracts these features from a particular images based on the four cells, the 4 classes that we have in our data sets. Then the model predicts the class probabilities, then it compares them the predictions are compared with the true labels of the images. Then we calculate the focal point, the focal length. Of course, the focal length helps us in managing the imbalance in our classes, since in our data set we had class imbalance. Then we had the back propagation, which computes the gradients. Then weights updated iteratively during the training. This is where we use the coarse kneading. Then how these models work? Yeah, for the B efficient net B4, as I said earlier on, all these models to work, of course, we have to have input, the processing occurs, then finally we have our 4 classes that are predicted. As you see there, all of them follow the same pipeline, where you input images through those layers. Features are extracted at multiple layers or depth. Then for particularly the efficient B4, the squeeze and the excitation models emphasize the important feature channels. Then the global average pooling aggregates the features. Then finally, fully connected layer predicts the class probabilities. Similar to both of these, for the interest of time, that's why I'm trying to just peruse through them. Now for the Swine transformer, how it actually works, it splits the image into the small patches like the tokens. Then it applies of attention within the local windows. Then it uses the shifted windows to allow cross-region interaction and build features hierarchically. So then for the RegNet, it processes the images through the convolutional layers. It extracts features. It extracts those features, then through, of course, the stacked residual blocks. Then let's go ahead. The optimizer, for the optimizer in this case, I used the Adam W optimizer. It's an adaptive learning rate of the optimizer. So for it, it updates the model weights in order to minimize the loss function. So here it also helps us to determine how, of course, the model parameters should change after each batch. So its advantages are adaptive learning rates, the weight decay regularization, then we have the improved convergence stability. Then additional optimization techniques. Of course, we had the coarse annealing learning rate scheduler, which is a strategy that helps us to adjust the learning rate during the training so that you can maybe decide to increase it or to decrease it depending, like smoothly. Then for the mixed precision, of course, this helps us to reduce the GPU memory usage as it speeds up training. Then for the weighted random samplers for class imbalance, it helps us to deal with class imbalance through oversampling the minority class and undersampling the majority class, hence eliminating bias towards the minority class. Then hyperparameters for the Swine transformer and the RegNet Y032 pipeline. The hyperparameter stock value, the batch size, of course, as we see there, it's 4. Effective batch was 16 using current accumulation times 4. The epochs were 25, but with a early stopping in case the model converges faster. The patience was 5. Then the learning rate is as follows seen below. For the interest of time, that is, those are the hyperparameters for the other models for the efficient net B4 and the ResNet 50 pipeline. Then for the results, of course, the swine transform model had the following: for the precision, the recall, the F1 score, the support for each of the classes. It had there the overall accuracy was 0.98. Then on the other hand, the RedNet Y032, it had an overall accuracy of 0.99 with the following one evaluation methods based on the precision, recall, F1. Then for the efficient net, it also had the overall accuracy of 0.99. Then equally to the ResNet, it also had the overall accuracy of 0.99, with all of them having different evaluation metrics based as you see there. Then rushing to the completion matrices, I see most of them gave a diagonal, gave most predictions along the diagonal, meaning the model accurately classified most of these images. So starting with the efficient net before, we saw there was only one cell that was classified as the red blood cells, but the rest were captured properly. Then for the leukocyte, it was really clear. Then there was no noise. Then for the plasmodium, we had 5 cells. That one of them were classified as Babesia, then the 4 as the red blood cells. Then also for the red blood cells, we saw 4. 1 was misplaced as the Babesia, then 3 as Plasmodium. Equally, this side of the ResNet, most predictions were done diagonally, meaning the model was performing a bit well, but it displaced actually 4 cells of Babesia, where it detected 1 as the Plasmodium, then 3 as the red blood cells. Then for the leukocyte, of course, it performed well. It didn't displace any of the cells. Then for Plasmodium, it misplaced 5 and predicted them as the red blood cells. Then when we checked the red blood cells, also we saw 4 of them being misplaced, 1 as Babesia, then the other Plasmodium. But evaluating this, the model, actually both of these models did fairly well, though maybe some fine tuning is required in order to see that this noise is actually catered for, to see that we remove it. Then on the other hand, we have the swine transformer and the RegNet Y032. All of them, most of the images were captured diagonally, but for the swine transformer, when we checked, I saw four misplaced cells. One that was predicted as the leukocyte, the other 2 as Plasmodium, then 1 as the RBC, which is the red blood cells. Then the leukocyte, it was clear none of the cell was misplaced. Then for the Plasmodium, 3 of them were misplaced as the red, or were predicted as the red blood cells. Then there was a lot of noise in the red blood cells, where 12 of the cells were misplaced and 5 were predicted wrongly, where 5 were predicted as Babesia, 7 as Plasmodium. Then checking on the other hand, we have the RegNet. RegNet performed well in Babesia, didn't misplace any cell, performed well in leukocyte, also tried to perform well in Plasmodium, but of course it misplaced as the red blood cells. Then for the red blood cells, we saw 6 of them, where 2 were taken to be as Babesia, then 4 as Plasmodium. Then Of course, most models tried well, but in conclusion, based on my training, the RegNet, of course, to the RegNet Y032 took the overall performance. So having the overall performance of the F1 score of 0.99, of course, it had only 9 errors with a Babesia recall of 1. Then the rest also, the local set was performed across all models. It was easy to classify them, and F1 had the F1 score of approximately 1. Then the Plasmodium was a bit hardest, where we saw mainly there was a confusion with the red blood cells mainly. So the trends are, of course, the RegNet, the efficient net, and the RestNet outperformed the transformer for the local cell level features, as seen in these confusion matrices. So with that, thank you for listening.